SwayamPrabha. Digital India. Educated India.
Hello, welcome to this lecture of Biomathematics. In the last few lectures, we have been discussing about diffusion. Like last couple of lectures, we discussed the diffusion equation, and then we discussed how do we calculate the RMS distance from this equation without really solving the equation. Even though diffusion equation was a second order differential equation, at this moment we will not discuss how to solve it. It's a little more complex. You need to learn some more mathematics to figure out how to learn this or to understand how do you solve this diffusion equation. But without really solving it, something very useful, some relation that is very useful we got, which is the RMS distance and time, the relation between time and the x square average. So this we will continue to discuss something about diffusion. Initially, the first part we will discuss a bit about another quantity, which is average, x average, and then we will go on to discuss another very important relation as far as the diffusion is concerned. So far we took diffusion coefficient as a constant. Today we will discuss what is diffusion coefficient related to? How is the diffusion coefficient related to temperature, viscosity, etc. of the medium? So this relation is the famous Einstein's relation. So we will discuss the Einstein's relation in today's lecture towards the end of this lecture. So the topic of we are continuing to discuss the section on applications of calculus and vector algebra in biology. And under this we are discussing this diffusion. So we said that if you take a tube, as you see here, if you take a tube and if you put a few number of particles in this or protein molecules at the middle of this tube, the concentration is only at t equal to 0, the concentration is only at the middle of the tube, and as we go along it will spread. The molecules will diffuse. Even at this time, maximum number of molecules, bigger number of molecules, the concentration is still more here at the center, but there are some molecules as we go along the tube to the left or to the right. So this is the concentration profile, and the diffusion equation is the equation that deals with this spread of this concentration is the diffusion equation. So the diffusion equation is dc by dt is equal to d del square c by del x square, where c is the concentration as a function of position and the time, and by solving this equation we expect to get concentration as a function of position for any time. That's what you will get. And we defined two quantities, x average and x square average, as x is c tilde average integral x c tilde dx minus infinity to infinity, and x square c tilde minus infinity to infinity as x square average. And we also saw that x square average is 2 dt. This is a very interesting relation, an important relation. The square of the position goes as time, or in other words, if you take square root both sides, the square root, the RMS distance goes as the root of time. So that's what the important relation that we saw, that is x RMS, which is this, is proportional to the square root of time. So this is x RMS is proportional to the square root of time. So this is the interesting relation that we found, and this is so this square root of time, or you can write this t power half. So this t power half is kind of synonymous to diffusion, one would say. Like it's like something moving like t power half, something moving like square root of time, that is called diffusive motion. So this is an important relation as far as diffusion is concerned. Now we will calculate x average, something which we are going to learn. So the question is, next question is, what is x average? So that is the question that we want to address next. What is x average? So we found that x in the previous lecture, that x square average is 2 dt. We discussed this relation. As we said, this is an important relation which says that how does the RMS distance, the root of this is x RMS, and how does the x RMS related to time. So the x RMS, if you take square root on both sides, the x RMS, as we wrote previously, look at here, x RMS is root of x square average. This is proportional to time, square root of time. In other words, x RMS is proportional to square root of time, or proportional to t power half. So now the next question is, what is x average? We will calculate the x average the same way as we calculated the x square average. How did we do that? We took this equation, which is the diffusion equation. We multiplied both sides by x. We are multiplying both sides with x and integrating. So you multiply here with x and integrating. So this becomes integral x dc dx with del by del t outside. And here also, we are, the right hand side also, we are multiplying with x and integrating. So integral x del square c by del x square dx. So we multiplied both sides of this diffusion equation with x and integrated from minus infinity to infinity. And what do we get? So the left hand side, as we defined earlier, is integral x c tilde x dx is nothing but x average. So this is the left hand side. So what do you get? You get on the left hand side. So let us look at what we get. So what we have is del by del t of integral minus infinity to infinity x c tilde of x dx is equal to d into integral x del square c by del x square c tilde dx. Now this part, as we said last time, is nothing but del by del t of, so del by del t, and this is integral x c tilde x dx is nothing but c average. So this is c average, this one, this part which is writing it in a box, this part can be written as c average. So this is equal to d into integral minus infinity to infinity x del square c tilde by del x square dx. Now just like we discussed last time, this can be written as integral, and you can take x as u, and this term you can take as del v by del x or dv by dx. So this is integral u dv by dx. So this is, you can do this rule in calculus called integration by parts. So integral, as we just discussed some time ago, integral as we just discussed in the last lecture, integral u dv by dx can be written as integral can be written as uv in the limits minus integral v del u by del x dx. So we can use this formula which is the standard formula in calculus, which we in the last class we figured out how this formula is coming. And let's say let us use this formula now. So what did we said is that we just said, have a look at here. So what did we just said, that del by del t of C equal to minus this, and we call this as u and this as del v by del x. So now we can apply this formula there. So if we apply this formula there, what do we get? So we have x as u and del square C by del x square as del v by del x. So what you would get essentially is this. If we apply this formula, what you would get is that del x average by del t is equal to u is x, so x, and v is del c by del x in the limits minus d into integral v du by dx. So now v is del c by del x, du by dx is 1. So this is what you will get. So this is what precisely I have written. What you would get is that d into x dc tilde by dx in the limits minus d into del c by del x del c tilde by del x dx. So this is what you would get. Now if you apply this limit, just by arguing that at plus infinity and minus infinity the derivative is, so by just arguing that this term you apply this del c by del x at plus infinity and minus infinity, and you calculate this term, you will get this equal to 0. So then what you are remained with is just, so this limit, this is 0. So what you have is just minus d integral del c by del x dx. So you have just this term. So now let us see what is this term, what this term gives. So let us think about that term a bit. So what you end up essentially is that del by del t of x average is minus d del minus infinity to infinity del c tilde by del x dx. So what is this? So this is derivative. So this is essentially minus d into c at the limits. If you take minus infinity and infinity plus infinity at the limits, if you calculate the c at infinity and minus infinity is 0. So the answer that this integral is essentially 0, because if you do this derivative, integral of a derivative is just the function itself. So you have c at infinity and c at minus infinity, they are 0. So essentially this derivative, this integral is 0. So you will end up with this relation that del by del t of x average is 0, which means that x average is 0. So what we got essentially is that x average is 0. We had found that x square average is 2 dt. So this is two interesting relations that we get, that x average is 0, x square average is 2 dt. Now what does this mean to say that x average is 0? Physically, what does that mean? So let us think about this. So let us think about this diffusing in a pipe example that we thought. So let us take this pipe, and to begin with you have some particles here, and let's say there is one blue particle here and one particle which I am circling here, which is in blue color. So let's say there is one blue particle here and all other black particles. Now if you look at this blue particle, and in one experiment you might see that this blue particle is going this way. So it will diffuse some distance x in this way in one experiment. Let's say you are doing the same experiment. Let's say you are doing the same experiment in a different day, or you are repeating this experiment. Now you have again, you start with the same condition. So now you have the blue particle you put here, when you put the blue particles becomes here, and this time it might move in this way. So it might move the distance x in this particular way. So if you just keep repeating this experiment of the experiment that we discussed, that is adding some amount of proteins at the middle of the tube and looking at where is it going, which way is this going. So at one experiment you might see that this, so basically what this is like, imagine that you have just one particle that we can detect, let's say it's fluorescing or it has some different color. So you will see that in one experiment this particular particle might be going this way, in another experiment this particle might be going this way, in some other experiment it might be going this way. So if you do many experiments and average over all this, so sometime it will go in the plus direction, sometime it will go in the minus direction. So minus direction, plus direction, and finally the average you will get 0. So the first experiment it might have moved minus 3 centimeter. In the next experiment it might have moved plus 3 centimeter. So if you just repeat this experiment many times, on an average, if you find the average of this, you will get 0. That's what it precisely means. It means that if you look, so if you in a diffusion experiment, if you look the position of one particle over many experiments, the average over all experiments will give you the average position as 0. On the other hand, if you calculate the square average, minus 3 square is 9, 3 square is also 9. So there is no way this x square can average out to 0. So you will get some quantity which is 2 dt. So the meaningful, since x average is 0, the meaningful quantity is x square average. This is the meaningful quantity that we should know, or that is useful. Physically useful quantity is x square average, in other words the RMS distance. So the important formula as far as the diffusion motion is concerned, it's x square average is 2 dt, or x RMS is equal to root of 2 dt. So this is the important formula. This is the root mean square distance that a particle would travel in a time t. If you do average over many experiments, this is the root mean square average that things would travel in a time t. Now, what is this d? So that is the question. What is d? We have been having this thing called d for a long time. So from this we found that d has a unit. If you dimension of d is length square by time, so it will have a unit meter square per second. So now what is this d? D is the diffusion coefficient. What does that mean? Diffusion coefficient mean? Diffusion coefficient essentially that contains the property of the medium in which you are putting this protein. If you are doing it in water, it contains the property of the water, like viscosity of the water. It also contains the temperature. So you can imagine that if the temperature is very large, things will diffuse out very fast. Higher temperature, higher diffusion. So the information about the temperature, viscosity, all the property of the medium is put into this one quantity called d. So the d contains the property of the medium. So now how do you find out how does the d depends on the property of the medium? If the viscosity is more, how does the d change? If the temperature is more, how does the d change? How do we find it out? So just by knowing what you learned in mathematics so far, and with some intuition, with some simple thinking, one can figure it out. Actually, this was discovered by none other than Albert Einstein in 1905. So this is what we are going to discuss. So the relation of the D, so the relation between D, temperature and viscosity, let me call this eta as the viscosity. So this relation is called Einstein's relation. So that's what we are going to discuss now. We will discuss this relation between diffusion coefficient, temperature and viscosity and this relation is known as the Einstein's relation. This was discovered by Albert Einstein in 1905. Albert Einstein, for his PhD, he was studying about Brownian motion of particles and he discovered this relation. I will tell you in a simple way how do we calculate, how do we derive roughly what Einstein did about 100 plus years ago, like about 106 years ago. Einstein derived these relations. As you might have also heard, this 1905 is a very famous year for Einstein. Like he wrote 3 very famous papers. One paper is related to this Einstein's relation, which became very famous, and this relation became one of the most popular relations, like very highly cited relations in science, because this has application on biology, in chemical engineering, in chemistry, in physics, in all sorts of fields. Einstein's relation related to diffusion is used in environmental sciences. In you can think of any field, virtually any field, and this relation will be, or is this relation is being used. And then he discovered he explained the photoelectric effect, and he also explained. He also had his famous paper on relativity. So these 3 papers made him world famous, like all these papers. So one of the paper even got him Nobel Prize. So this was a miraculous year as far as Einstein is concerned and the world of science is concerned. So we will discuss one of his contribution in that year, 1905. It is interesting that just by understanding this simple mathematics we can derive this relation. It is very similar to what we did for Nernst equation. So we will go in the same line as we went for to understand Nernst equation. So let's go ahead and think about Einstein's relation. So Einstein thought about the following example. So he thought there are some particles in water in a beaker, and this particle is subjected to some external field. So let's say there is gravity downwards. So if there is gravity, if all these particles with some mass, they will be forced to come down because of the external force, gravity for example. It could be either gravity, or it could be, if they are charged particles, it could be even electric field. So you could think of this as electrophoresis if you wish. So basically you could even think of this as charged particles, and then there is some force exerted on this charged particle due to electric field. This could be like some protein molecules under electric field. Now let this force be minus g times x. Mathematically this force is minus g times x, where x is the distance from bottom to top. So x is the distance starting from the bottom to the top. So x cap has this particular direction and the force has this particular direction. So force is acting downwards and the distance is going upwards. So the F and X have opposite direction, that's why this minus sign. So G is the amount of force. So G could be the amount of electric field, electric force due to electric field. It could be amount of force due to gravity, whatever you wish. But G is some force and the magnitude of the force is G, and F is the force, the vector force. So let F is equal to minus Gx. So we can say that the energy, so for every particle, if you want to this particle to go up at distance x, it has to spend an energy F dot x. So if you have a force F, so look at here, you have a force F, so which is, let's say, let's say it is G x cap, and let's say that the energy, so if you have such particles and each of these particles is experiencing a force, so if this particle wants to go up a distance, if it wants to reach a distance x from the bottom, it has to spend an energy F in F dot x, so which is nothing but F is minus G x cap dot x, so this is minus Gx. So this has to spend this much energy, so it is not favorable. So the magnitude of energy is Gx essentially, sorry, the energy is Gx, so it is not favorable to go up here because the force is in this way, so it has to spend an energy. So most of the particle you will find at the bottom because there is a force acting and there is an energy cost to go here. So if you look at the concentration, if you think intuitively, the concentration will be more at the bottom and less at the top. You can think of any particle, if you put something into water, you could think it of as sedimentation, something will fall down to the bottom of the beaker, right? If you put some something which is some objects into water, they will fall down because the gravity is attracting it down. So the concentration if of anything will be more at the bottom and less at the top. So if you plot, if you wish, if you plot the concentration as a function of the distance from the bottom, you will see some exponential relation. There is some reason why it is exponential, but let us intuitively assume that C is proportional to e power minus Gx by kBt. So Gx is the energy and it has to be divided by another energy kBt to make it dimensionless. So the concentration decreases as you go along x, this is what it means. So if you know this relation, we can derive the Einstein's relation. So this is the one ingredient that we need to know, that the concentration will exponentially decrease as we go to the bottom. How do we get this relation? That we will discuss later, but for the moment just take this relation for granted, which is intuitively clear to you that the concentration will decrease as we go along x, and knowing this we will derive Einstein's relation. So let us say the concentration will be more here and concentration will be less here, and this has this particular functional form. Once we know this, we will follow roughly what we did for deriving Nernst equation. We said that in the case of Nernst equation there is a current due to electric field or the force. Similarly here there is a current due to this force, this gravitational force or electric force which is pulling down these particles downwards. They will want this particle to flow down. So the flowing down happens with a velocity v, and this v is related to the current or the flow j, as we discussed previously in the case of Nernst equation. Jf is c concentration times v, which is velocity. Now any particle moving in water will have a velocity which is given by f by 6 pi eta a, where f is the force acting on that particle, pi is a constant, eta is the viscosity of the water or the medium, and a is the size of the particle. So there are quantities which you should remember. Eta is the viscosity, A is the size of the particle, and F is the force acting on this particle. If you know this much, the velocity is this, and the flow is proportional to the velocity. The more the velocity, the more the flow is. So the flow downwards is C times V. So this can be written in a different way, the C times V, and V is force. This can be written as minus Gx cap, where x cap is this direction, so minus Gx cap. So substituting this F as minus Gx cap, you get Jf, the flow, as minus C Gx cap by 6 pi eta A. So this is the current that is making, so this is the flow due to this this force. It could be gravitational attraction downwards, it could be the attraction due to electrostatic forces or electric field, it could be the electric field applying downwards, forcing the proteins to move in this particular direction. So this could be any force, whatever the force you wish, but that force will lead to a current or a flow given by this particular formula. As we saw in Nernst equation, we had similar flow. Now, this flow leads to one interesting thing, that it makes the concentration more here and the concentration less here. If the concentration is more here and the concentration is less here, diffusion can happen, because diffusion is a flow from higher concentration to lower concentration. So in principle, things can diffuse back from here to here. It can diffuse back from lower concentration to a higher concentration. So here it is, it can diffuse back from higher concentration to a lower concentration. So here it is higher concentration, here it is lower concentration. So from here to here, you can imagine that there can be some flow due to diffusion or flow due to concentration change. You could think of some kind of diffusional or diffuse flow. So how much is that flow? So we said that due to diffusion there can be a current or a flow, and that current Jd is related proportional to the derivative of the concentration. As we saw previously, Jd is proportional to del C by del x, and as we go along the x, C decreases, so del C by del x is negative. So with this minus sign, the flow is actually along the x cap direction, which is in this direction shown by this blue arrow. So we have a diffusion which is basically taking this in this particular way. We have a flow which is in this particular way given by Jd equal to minus d del C by del x. Now what is C? We just saw that C is proportional to e power minus g. So we just said that C is proportional to e power minus gx by kbt. So that means C is some constant A, it will be some constant, times e power minus gx by kbt. Now we also said that J is minus d del C by del x. Now what is del C by del x? Del C by del x of this will be, so let us find the derivative of this. So what is the derivative of this? So del C by del x will be, A is there, derivative of E is e power minus g itself, this itself, times the derivative of this, which is minus g by kbt. So we said that derivative of e power kx is k e power kx. So we had a k which is minus g by kbt. So that is the k which is coming here. So, by using this relation that we learned, the derivative of e power kx is k e power kx, where our k here, in our case the k was minus g by k b t. We have del c by del x is a e power minus g x by k b t into minus g by k b t. Now, look at here, what is this a e power minus g x by k b t? What is this part? This part is c itself. Look at here, this is c is a e power minus g t x. So, del c, c is a e power minus g x by k b t. So, this is c itself. So, del c by del x is nothing but c itself times minus g by k b t minus c g by k b t. So, what does this mean? This implies that we had j, which is d del c by del x, is minus d times c times g by k b t. J is minus d c g by k b t. So, that is what we have here. So, j d is d del c by del x, and substituting for d, known that c is proportional to e power minus g x by k b t, and substituting this in this, we get j d is d c. There is a plus sign here. I made a mistake, and there is a typo in this. So, if you just substitute this minus, there is a minus sign here. By taking this minus sign into account, we will get a plus sign here. So, essentially you get this, what is shown in this square, in this rectangle here, what is marked here, the current upwards is d c g by k b t along the x cap direction, and we had j f downwards and j d upwards. So, we had current downwards and current upwards. So, when you have currents in opposite direction, we said that when both these currents balance, that the current upwards and the current downwards, when they balance, we reach equilibrium. We call it equilibrium. For example, if you look at this particular point, there will be some current upward, there will be some current downwards, and when these currents balance, we have net current 0 and we reach equilibrium. This is exactly the argument that we discussed in Nernst, in the case of Nernst equation. So, what does that mean? Equilibrium means net current 0, net current is nil. What does it mean? The total current JD plus JE is 0. In other words, JD is equal to minus JE. Okay, there is what I meant here is JF. This is a typo here, it should be JF here. So, what I meant here is that JD plus JF is 0. In other words, JD is equal to minus JF. So, the current due to the force is equal and opposite, it's equal with opposite sign, that of currents due to the diffusion. So, this is what this is the condition for equilibrium. So, let us try doing this. So, what we have is JD as dCg by kBt and JF as minus Gx by 6 pi eta a, and we want JD is equal to minus JF, and that means dCg by kBt is equal to Cg by 6 pi eta a. So, which implies I can take everything, d alone keep this side and take everything else to the other side, and what you would get is that d is equal to kBt by 6 pi eta a. So, this is says that diffusion coefficient is equal to kBt by 6 pi eta a. So, this is the famous Einstein's relation, that this relates the diffusion coefficient to Boltzmann constant, temperature, viscosity and the size of the particle. What does it say? The more the temperature, the more the diffusion coefficient, the more the viscosity, this is inversely proportional. So, if viscosity is very large, the diffusion will be less, which is intuitively clear. Something might diffuse better at water and much less in honey, where honey has higher viscosity compared to water. So, the viscosity of something highly viscous, let us say take example of tar or honey, it will be very difficult for things to diffuse in tar or a very highly viscous medium. And if the size of the particle is very large, if you look at the size, A is the size of the particle. If you have proteins that are very huge, very large, they will not diffuse. The diffusion coefficient of those objects will also be very small. So, this is the famous relation called Einstein's relation, which relates the diffusion coefficient to these quantities. And the relation, we derive this relation by the way we derive Nernst equation, by arguing that if you have an object, if you have a beaker and particles under a force F, there will be two currents. The concentration will be more here because of this force is attracting it downwards and very few particles up. So, since the concentration is less here and concentration is more here, there will be diffusion this way, diffusive current and the current due to the force, and when they are equal and opposite, we get, by arguing that they are equal and opposite and equating them, we get this relation, which is D is equal to kBt by 6 pi eta a. So, now we learned three things. We learned that x average is 0 in today's lecture. In the previous lecture, we learned that x square average is 2 dt, and we also learned that D is kBt by 6 pi eta a. This is true for a spherical particles typically. If this is not a spherical particles, this 6 pi eta a could be something else. But however, let us limit ourselves to a case of spherical particles. Proteins could be thought of as a spherical particle. So, this is another relation that we learned today, and these are the three important relations as far as diffusion is concerned. And using simple arguments from calculus and vectors, we could derive these relations, and this has very high significance as far as diffusion is concerned. Now, so one more interesting thing I just want to share with you is that, so in the beginning we graphically represented the diffusional profile, the profile of the concentration in this particular manner. Now, what is this mathematical function that can represent this concentration? So, it turns out that the mathematical function C of x is, in the case of pure diffusion, that diffusion with no force. This is not the case. So, in the case of diffusion with force, we found that this is e power minus f x by kBt. So, this is diffusion under external field, but when there is no external field, that is diffusion under no external field or free diffusion, C of x will be having some form which is a e power minus some b x square. So, this function is called Gaussian function. This has a bell-shaped curve. This is a bell shaped curve if you plot this. So, this is called a Gaussian function. So, this is diffusion, this is free diffusion. There is no external this is free diffusion, and the free diffusion is, now if you plot this, we saw that this has this particular form, and if you plot this, it will have some form which is symmetric like this. I am not properly drawing it. Just go and see how the Gaussian plot this function if you wish, like putting some values for a and b, plot it yourself and see how does this look like. It looks like a bell shaped curve, symmetric both sides to the x axis, nicely symmetric around the peak. Now, the free diffusion is governed by this equation del c by del t is equal to d del square c by del x square. It turns out that the diffusion under some external force is governed by the following equation. So, we have this equation plus some effect due to the external force. So, let us say the particle when they have an external force. So, if you have just no force, this will be the equation, but let us say each of this particle is experiencing some force downwards or in a particular direction, then each of this particle will get some velocity due to this external force, then the equation will be this. So, this is the diffusion equation under an external force, and this is free diffusion where there is no external force. So, these two are two equations, and this equation has a solution which is of the form this, and this equation has a solution of the form this. So, we will see how do we get to the solution of this later. If we may see this, how do we get this relation, but for this, at this moment we wouldn't go to solve this equation. We will just understand that there are such differential equations. When it comes to probability, etc., we might revisit these equations in a different context, but at this moment it's suffice to say that these are very interesting equations in biology, and there are two importance relations that, as far as these equations, from this mathematics, essentially you get three importance relations which you should all remember. That is the average distance that a particle moves. If you just mark a particle and ask the question, if you do many experiments by marking a particle and ask the question on an average where it will go, sometime it will go to the 1 x minus x, some other time it will go to the plus x. So, on an average it will not go anywhere, x average will be 0. That is what this means. But the x square average is 2 dt, and the diffusion coefficient is kBt by 6 pi eta a. So, by knowing these relations, with these relations we will summarize today's lecture. So, the importance relations are x square average is equal to 2 dt and d is equal to kbt by 6 pi eta a. You will come across these relations many times in your life, and with this we will stop today's lecture. Remember these relations, and with this we will kind of completing the section on diffusion. We will go ahead and learn new things in the coming lectures. With this we are stopping today's lecture. Thank you.